Great to see you here again. We are still in the first chapter. We're basically talking about logic and proofs, the foundations of them. And in this new session, we are going to look at compound propositions. In the previous session, I defined the propositions. What are they? How do we deal with them? We had the truth and truth values of those propositions. And now we are going to look at compound propositions. But let's have a look at the definition of a compound proposition. A compound proposition is a new proposition combining existing propositions with operators. So we have those existing propositions, and now we're going to create a new proposition, which is in fact a combination of previously defined propositions. And we combine them using operators. We will look into the different type of operators that we have, and we will see how they influence the propositions, the new propositions. Let's first have a look at the definition. Definition one, the first definition is where we have a proposition P, and we look at the negation of P. And P is the negation of P is denoted with the special symbol with P, or P with a bar above. So the negation of P is in fact not P. Let's look at the previous proposition we had. We said Prague is the capital of Czechia, and we say not P means Prague is not the capital of Czechia. Now we have to look at these elements and we have to see what does it do to the truth table. And when we have a truth table where we have the propositions evaluate about their truth, we can have the truth table for the proposition P and not P. When we look at P, P can have two truth values, true and false. Not P are in fact the opposites, and when P is true, it means that not P is false, and when P is false, not P is true. So these are the elements that we can combine, we can use them, and we can define the truth table for P and not P. In the second definition, I'm looking at the conjunction. And the conjunction is a special relationship, compounded proposition, when we have two propositions P and Q, and we noted P with the inverse triangle Q. It means the conjunction of P and Q, it means that P and Q is true when both P and Q are true. For example, we have the statement Prague is the capital of Czechia. Then we have Q, look, it's me, lives in Prague, I live in Prague, Prague is the capital of Czechia. So when we have the conjunction of P and Q, since both P and Q are true, we can say that the conjunction P of P and Q is also true. Both are true. Now we can look at the truth table. We can look at the truth table for conjunctions, and we start in fact with the two propositions P and Q. So for P we have true, true, false, and false. And we have to find all the possible combinations. We have P true, Q true, P true, Q false, P false, Q is true, P is false, and Q is false. And now we have to say, what's the conjunction? What does it say, P and Q? When P and Q are true, both are true, it means that the conjunction is also true. Now, the next one, P is true and Q is false. It means not both of them are true, so it means that the conjunction of P and Q in this case is false. And we can conclude the same for P being false and Q being true, then the conjunction is also false. And it is clear when P and Q are false, the conjunction will also be false. Let's have a look at another operator. And in definition 3, we again consider propositions P and Q, but now we look at the disjunction. And it's noted P inverse triangle Q, and this means, or it means that the disjunction of P and Q is true when P or Q are true. When one of them is true, the disjunction of P and Q is true. Let's have a look. P is the Prague. Prague is the capital of Czechia. We know that this proposition is true. Another proposition, Q, look, me again, lives in Antwerpen. Now we already know from the previous case that I live in Prague. So it's clear that Q, in this case, is false. But when we look at the disjunction of P and Q, we see that the disjunction is true because at least one of those two propositions is true. Let's now look at the truth table for the disjunction. When we look at the truth table, we have again the same values like before, but now in the third column we have the disjunction of P and Q. So one of the two has to be true to have a true disjunction. So first of all, P and Q are true. It means at least one of them is true. So the disjunction is also true. T and F and T, we see that here with the disjunction at least one of the propositions is true, so that it means that the disjunction is also true. And the last one we have false because none of them has a true value. Both of them are false, so we don't have the minimum conditions that at least one of the propositions has to be true. So basically the disjunction of P and Q is false. Let's define another, third operator. We look at the propositions P and Q again, and we look at the exclusive P and Q. And this is noted as P with a circle with a cross in the center and Q. And this is true. The exclusive OR is in fact true when either P or Q is true. So we have one and only one has to be true. When two are true, the exclusive OR is false. And of course, when both are false, the exclusive OR is also false. Let's come back to Prague is the capital of Czechia. Luke lives in Prague. So what does the exclusive OR say? Both are true. And in this case, the exclusive OR of P and Q is false. Because both of them are true, it means it's one too many. It can only be one. Now let's have a look at the truth table for the exclusive OR. And we look at the table, the same table again, where we have P and Q, the same values, the same truth values as before. And now we have to look at the exclusive OR for P and Q. We already know when both are true, the exclusive OR is false. Now we have the two second ones, T. Now we have P true and Q false. This means that only one of them is true, so we have the true value for the exclusive OR. Then we have P false and Q true. So again, we have a true value for the exclusive OR, and then in the last row, we have P and Q false. So none of them is true. We don't have the minimum condition. So the exclusive OR is also false. So that was the definition about the different elements. And let's have a look now at a combined table. We look at the table for the conjunction, the disjunction, and the exclusive OR. So basically here in this table, in this truth table, we find the different elements, the different operators combined. So first we have again the truth values for P and Q. Then we have the truth values for P and Q. We have the truth values for P or Q. And we have the truth values for the exclusive OR of P and Q. So these are the basis for the coming exercises. And in next video, we will be looking at the different elements. We will look at the third paragraph of the first chapter, and we will look at the conditional propositions. We will be using the truth tables to identify the conditional propositions, to find out how these conditional propositions are defined and how we represent them in the truth tables. Another session which is finished, so I'm looking forward to seeing you in the next video. Thank you and bye-bye.